Hello, everybody. Welcome to the digital event, Is Modern Chemistry Rubbish?, hosted by De Gruyter. Thank you to everyone who has registered and logged on to Zoom to participate. We are excited to co-present this event with Worcester Polytechnic Institute. Please note that this panel discussion is being recorded. The recording will be made available for participants to watch and share later. Those who are joining will have their cameras and microphones turned off for the duration of the event. Only the panelists and the moderators will have their cameras and mics on. For participants who have questions for the panelists, please enter them in the chat function. We will read and answer them during the Q&A portion. The digital event will begin with presentations from Worcester Polytechnic Institute professor and author Rob Krueger, who will then pass the floor on to Chris Slootweg, professor from University of Amsterdam. Here, Chris will talk about the role of chemistry within our modern society. From this presentation, the moderators Helene Chavaroche, acquisitions editor at De Gruyter, and Anita Mattson, WPI professor, will form questions around the content. These questions will be posed to our panelists, Alexei Lapkin from the University of Cambridge and Dr. Juliana Vidal from Beyond Benign. We will have 50 minutes of discussion and 10 minutes of Q&A. De Gruyter is an independent publisher with a large portfolio in STEM. That's more than 1,000 books and 1,600 journal articles published each year. We also have around over 30 international publisher partnerships, and we focus heavily on subject areas including chemistry, industrial chemistry, material science, physics, computer science, and engineering. If you have an idea for a book or journal article, please do not hesitate to contact Elaine. Now, without further ado, please welcome our moderator and panelist, Robert Krueger.
Good day, everyone. My name is Rob Krueger. I'm a professor of human geography at Worcester Polytechnic Institute in Massachusetts, USA. I'm joined here with Anita Mattson, who is a professor of chemistry at WPI as well. And she and I are the co-editors of the Integrated Global STEM series, which is a partnership between De Gruyter and the WPI Press. As you heard, the title of today's talk is Modern Chemistry Rubbish?, which is a play that was published in Nature Reviews Chemistry in late last year. And we have a number of, as was pointed out, special guests and speakers today. And so without further delay, I would like to turn this over to Dr. Chris Slootweg, who is at the Hof Institute for Molecular Sciences at the University of Amsterdam in the Netherlands. Chris?
Thank you, Rob. I'll share my slides. It should be visible now, right?
Mm-hmm. It is.
Perfect. So let's discuss the role of chemistry in our modern society. And I'd like to start off with this picture that was published by the Ellen MacArthur Foundation about a year ago. That if you, for example, think of the energy transition, obviously you desire renewable energy. But to realize and complete the energy transition, what the Ellen MacArthur Foundation rightfully puts on the menu is that we can only realize this by completing the energy transition also with the circular economy. So in short, if you would need windmills, solar cells, batteries, all of those materials needs to be continuously recycled and regenerated. So this is the key mindset for my short talk. So let's start here. So think back a few years, maybe a few more years, and think of the origin of life. And imagine Charles Darwin describing this warm little pond where there are 6 key biogenic elements that are highlighted in the title. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur came together and really originated life on planet Earth. Now, these 6 elements are still today our key biogenic elements. So for sustaining life on Earth, they're essential. Now, my proposition today is that you may call these 6 biogenic elements not only the origin of life, but also the origin of waste. So imagine this climate change wave upcoming and the bigger one connected to biodiversity collapse. My proposition is those are directly related to SNOPs, to the biogenic elements, but then because of their excess waste in the environment. So let's look at this cartoon in a bit more scientific fashion. Here is a picture that highlights the planetary boundaries published by the late Stefan and Röckström and colleagues, and frequently updated. And this picture basically shows planet Earth and highlights at the outset the what I call global waste problems. So green, think of this as a traffic light. Green is good, yellow, orange, not so, and red means immediate action is required. And thinking of the waste problems that are highlighted in yellow and red are climate change, phosphorus and nitrogen are key nutrients that are also entering the environment in excess, and their direct connection to biodiversity loss. Now, we can actually map the 6 key biogenic elements to these global waste problems. So climate change connected to CO2 and methane, phosphorus and nitrogen connected to the full redox chemistry of the element of nitrogen, as well as phosphate. And all of it, like I said, it connects to biodiversity loss. Now, the pictures, as always, 1,000 words. And so imagine that phosphates, other nutrients that are nitrogen-based, like ammonia and nitrate, enter the environment. Then I always say once a fertilizer, always a fertilizer, but we don't need too much algae at this place in the environment. So this has a direct link to the so-called dead zone and a reduced loss of biodiversity. And not only some of the elements like phosphorus are slowly depleting. They're depleting reserves. So this is clearly not the right way of doing chemistry and implementing the use of nutrients on a global scale. We know this issue for quite a while. So this short paper published in Nature highlights in 1944 this disturbance of the phosphorus cycle in nature, showing the direct link of man-made phosphates for food production and the excess release of that in the environment, causing algae blooms, for example, as illustrated over here. The same goes for carbon. And so in this news article from New Zealand, 1912, so you can read the direct link of coal to CO2 to climate change. So we know these issues for quite a while, and apparently today there is still a lot of work to do to mitigate these issues. So while I was listening to this album by Blur, Modern Life is Rubbish, and looking at the cover that really shows a steam engine train that uses coal, converts it into energy and waste CO2 that is emitted in the air, I thought, well, looking at these global waste problems, still today we are in need of a bit more sustainable chemistry. So you can actually pose the question: is modern chemistry rubbish at the moment? And I quite like it that this was published in this journal, where you can say that nature, that should inspire us how to develop circular systems, develop sustainability, that nature has reviewed chemistry, and this is the outcome. Modern chemistry is rubbish. Obviously, not all chemistry is rubbish, but given the work to do in sustainability, this is what you could say. So change is needed. Hence this quote by Albert Einstein. So we really need a new paradigm, new way of thinking how to use our materials on Earth, and how to make products that we need a bit more sustainably. There is more though. So if you look at the other pillar of this planetary boundary concept, the novel entities are basically the man-made chemicals, molecules, materials that also slowly but surely enter the environment. Think of plastics, think of herbicides, think of pesticides, and for example, PFAS, so persistent fluorinated molecules that accumulate in the environment, and they are toxic and cause slowly but surely negative consequences. Thinking of those fluorinated molecules, it's actually interesting that zooming in on the FDA-approved small molecules drugs approved, that 3 years ago of the small molecules, quite a few had carbon-fluorine bonds. So quite a few PFAS drug molecules were approved. Now, obviously, we need better drugs for curing our diseases, but we also should realize that currently there's an ubiquitous occurrence of active pharmaceutical ingredients in the environment, their metabolites in the environment, and also their transformation products. So clearly we need to do much better in terms of the design of these sorts of molecules. So when 2 years ago, this beautiful molecule was published in Science, this perfluorocobubane, that you can add an electron, you can study its properties. And as a physical organic chemist, this is gorgeous chemistry. But Chemical Engineering News highlighted this molecule as being the molecule of the year. And it's a PFAS molecule. And I thought that is a bridge too far, because for being a molecule of the year, we also need to include its environmental impact and possible consequences. Hence the title of the piece that I published earlier that we just discussed. Now, my ideal is really to develop this circular economy and how to do that. So currently we're in the linear economy, where we take resources, make products by doing chemistry as sustainable as possible. But at the end, many products, they enter the environment and are not recycled at all. So you can design recycling loops, but it's much better, much more efficient to focus on a complete redesign of any molecule, any material that we need, and design it such that it has its function, but also design a closed loop system where we can continuously reuse our materials. Now, what are the principles, the guiding principles that there are out there? I mean, obviously, the green chemistry principles, more than 25 years ago, Paul Anastas and John Warner highlighted the green chemistry principles, and they truly help us in designing more sustainable processes. Even in the Netherlands, at high school, every pupil learns and applies these principles. But you may wonder, is this all that we need to generate a sustainable society? And some highlight that if you use a renewable feedstock like biomass instead of fossil fuel, that by definition, the process is sustainable and the product is sustainable. And there, I think we can use a bit more data to really quantify sustainability. Because, for example, what I would prefer to see renewable feedstocks as just using a different feedstock, fossil versus renewable. And then we need to quantify sustainability and also fully analyze which waste problem we're tackling. Because if we only change the resource and still make the same product, then it could well be that by changing the resource, we're not solving the waste problem at all. And so it's really important to analyze which resources are suited and what is actually the sustainability challenge that we're tackling. Now, what we concluded is that the green chemistry principles are really important and essential to optimize every single process that converts resources into product. But then, how do we develop such a circular economy? And what I really find interesting is that the first cycle, if you make a plastic bottle, for example, there is a true difference between using biomass, CO2, or fossil fuel, for example, in making that plastic bottle. Well, for the second cycle, the third, fourth, and so on and so forth, it's truly the product that is your starting material. So I would advocate for a shift in focus on resource to a full shift in focus on the product. And let's design products such that they behave as we want them. They have their function, but also design them such that they also can really be handled efficiently in a circular economy. It's much more resource efficient, and then it's also much easier to recover and reuse those resources. And this basically has led 5 years ago to another set of 12 principles where it's most important to highlight the design of products, and of course to focus on the recovery of materials after their use. And now I would actually say waste is really a word that sticks to the linear economy. So it's much better to collect and use products to keep the value high. And as a last resort, then let's at least recover the waste and reuse it. Now, if you think of some examples, how can we tackle these, enormous global challenges? I mean, think of climate change. One option is to basically develop an end-of-pipe approach. Let's capture CO2, let's capture methane, convert it into useful products. But the other, maybe even more efficient, is let's stop emitting greenhouse gases in the first place. So let's develop an energy system that is circular and that has no emissions by default. I mean, that would be ideal, to use clean energy, clean hydrogen, and no emissions in the first place. Now, the other is, for every product, you need need a different approach. If you think of nutrients, we will always require nutrients for plant growth. So we always will require nutrients for food production. So there, it's essential to recover those nutrients, stop entering them in the environment where they're not needed in excess. Let's recover them and let's recycle them, use them in closed loop systems. So that's really designed for recycling. That is essential. And then this picture actually is not a problem, but is actually an opportunity for developing a circular nutrient economy. Now, if we zoom into novel entities like medicines, like drugs, particularly the ones that cure diseases, then it's sometimes not efficient or not even possible to design a closed loop system where those materials in small amounts are recovered from complex waste streams like our sewage system. So those molecules, like the fluorinated active pharmaceutical ingredients that I showed before, those should be designed such that they work in the human body, but at the end, that if they enter the environment, that they mineralize, basically that they degrade into harmless elements or basic molecules that can enter the key biogeochemical cycles. So next to green chemistry, circular chemistry is essential. And I like to add safe and sustainable by design, as they're really the design of every single product that is essential. And that should be designed such for its function, what we already do nowadays, but we need to include non-toxic circularity as well. And then it really becomes multidisciplinary, even interdisciplinary, where you combine the making of materials, the design, but fully incorporate the environmental impact. And with that, this is my last summary slide. I mean, chemistry, as far as I'm concerned, really becomes truly benign if you fully focus on these three pillars. So sustainable green production, where the focus is on efficiency, where the focus is on the design of functional molecules and materials. But that needs to be added to the design of circular products that are either durable, reusable, or can be recovered and recycled with the aim of becoming much more resource efficient. But also that is not enough. We need to add the third pillar, where we at all times focus on safety, so human, animal safety, and environmental safety. And with that complete picture, I'm pretty sure we can redesign chemistry, that in a modern society, it becomes the pillar for designing a sustainable society. So with that, I'll stop sharing and look forward to the next part of this webinar.
Thanks so much, Chris. That was awesome. So as we were organizing this webinar, one thing we really loved was the title of your opinion piece, that modern chemistry is rubbish, that you had wrote for Nature Reviews Chemistry. And you did mention it in your presentation a little bit, but I was wondering if you could elaborate a little more, why you would pick a title that might elicit, such an emotional response in people. If that was your goal, and if so, why?
Well, it was basically my expression of concern. It was in the time of a global pandemic that I was penning down some thoughts. Nutrient crisis in the Netherlands. We have a major nitrogen problem. Phosphate crisis in the US, for example, is in the news often. There is so much going on basic elemental chemistry that of which the materials are wasted. So I thought, we need to change the mentality of the industry. We need to change our habit of using valuable resources. And I was listening to that Blur album, where on the cover, the problem of our way of using resources was highlighted. So then I said to myself, modern chemistry is rubbish. And obviously not all chemistry is rubbish, don't get me wrong, but I kind of liked it that it was accepted in a journal that also highlights Nature Reviewed Chemistry. You've been punt and do better, please. And it's really a message to all, like focus on education, focus on change our habits in industry and society, and we can do a lot better. And let's learn from the past, and hope that was the objective. Hope this piece helps a little in that direction.
Thank you.
I have the next question, Chris. I'm going to take a minute to comment. Fake Plastic Trees by Radiohead might be something that could provide some additional inspiration.
Yeah, another of my favorite bands.
I'm wondering, having said, I don't even know what a fake plastic tree, metaphorically, but I don't know what a fake plastic tree would look like. And so, Chris, I want to ask you first, and then Alexei second, is, where would you like to see the field of circular chemistry integrated into industry? Just, as you say, beyond the hood and the graduated cylinder into real life.
Yeah, for me, it really started with hearing of the concept circular economy, and then realizing how is this happening, and then realizing we need also new technologies, a new mindset to realize this. So then the next step, I would find it awesome that we truly start designing our products such that they much more efficiently can be used in closed loop systems. If you mention plastics, obviously you can change the resource, But if the problem is at the wayside that we don't collect it efficiently and reuse it efficiently, then maybe we should only, allow the plastics that can be recovered and recycled easy. And this is this is a paradigm shift for the industry who makes even low value materials on high scale. But I think that this true change is required, because only we change the symptoms, but maybe not the problem.
Thank you. Alexei.
Rob, so your question is about where do I see the chemistry of circularity? And Chris has highlighted where at least Europeans are thinking about in terms of the new paradigm of, or what hopefully will be the framework of safe and sustainable by design. This I fully accept that this is what needs to be the new reality of chemistry, but it needs to be done supported by evidence, basically. And many of the problems we have at the moment is because we didn't have the data. In many of the industries, if you want to have good business intelligence and business systems and optimize your systems, and we are going to be optimizing for better resource utilization, that's not possible if you don't have the data. And in chemistry, that's actually the biggest problem. We don't have the data. We don't have the data along the supply chain. The supply chain is extremely fragmented, very secretive. We quite often don't know what's in our products. Again, plastics is a particular problem. If you want to know what's in your children's plastic toys, you will never find out. And many of the things which are there, you really don't want to be your child holding those. That has been publicized quite widely. But that is a problem. It's not necessarily the chemistry, though, problem. So the chemist will invent really amazing things and will solve the problem. The real problems are mostly in regulation and what the design criteria are set. So if you set the design criteria to be functional and benign, the design will be done to be functional and benign. It's just those were not the criteria until we're just talking about this now, that this should be the equally weighted criteria.
Yeah, I fully agree. And also to educate every pupil in chemistry and beyond to develop chemistry as such. Because I mean, in many chemistry curricula, the focus is on all the various disciplines, converting resources into product, and that's it. But like you explained, Alexei, that is not part in most curricula. So we also need to change the way we educate everyone, and then that knowledge can be pushed to society, into industry to further develop.
Yeah, for some reason.
Sorry.
Product design is taught to chemical engineers, but not necessarily to chemists.
Exactly.
But with this knowledge, can, I guess in some ways, the tail wag the dog? Can chemists reshape the way industry goes about the way it does things, based upon the cult, I mean, what you're talking is you said a paradigm shift, a cultural shift in how we think about chemistry beyond the thing, and what its life cycle might look like. Can the tail wag the dog? Is this, I mean, going to another rock band, the Flaming Lips, the Spark That Bled? I mean, is this something that is going to go poof and then nobody's going to hear it? Or how are you going to push that agenda forward? And you mentioned by teaching students for one, but how do you, that design question is another one. Do we need to teach chemists about design?
I can jump in. Sorry, I'm just sorry. So about in terms of industry, I can say that from the beyond benign side, because we're a nonprofit dedicated to green chemistry education, circularity, sustainability, all the things that Chris mentioned already, they're important for on this very molecular level design, like chemists in the lab, what they can do to promote sustainability. And we work a lot with industries, and all the time they're like, we need chemists not only with the abilities to solve the technical challenges that we have, but also to have this background in green and sustainable chemistry. So whenever they go to industry, they know how to solve these problems already. And we have a lot of industries they're supporting green chemistry education because it's easy to teach them already, instead of teaching them whenever in their industry of like what they can learn afterwards. So if this is embedded in the chemistry curriculum, it's way easier. And I think we can see the consequences in a fast way, a way faster than what we actually are seeing right now, and that in a way that we need to see. Sorry if I said too many things, but I think
No,
I think
I appreciate
education is
that.
fundamental.
I once published a paper from where we looked at the American Chemical Association in 1939, where they knew about the hazardous impacts of that, and there was no connection between chemists and government and regulators and things like that. And so the things that you're talking about are really important to really making this something bigger and becoming part of our daily discussions.
Yeah, and it really requires system thinking. You know, it requires a new generation of scientists, of ambassadors that can, you know, understand how molecules and materials are created, but also what the environmental impact should be, and how it's assessed and how it can be changed. And like the example of the drug molecules that I mentioned, I mean, yes, for their function, I mean, it could be essential to have fluorine bonds. But if you follow them, how they enter the environment, maybe we should include, you know, the benign factor a bit more into the design. And the regulation that Alexei said is a strong one, because that pushes ideally globally the industry.
Maybe I'll just correct a little bit in the sense that the chemist is not really the end point, or not the tail, because we make molecules to be used as in products. So the consumer defines the function, or the market defines the function. Chemists design molecules which fulfill a certain function. So that's where the connectivity is. So you can fulfill the functions in many different ways, not necessarily with molecules, but it depends then what technology will develop and how it's going to be done. And we have examples in related industries, for example, in textiles. If the designers start to demand that dyes, for example, are much cleaner and much more sustainable, that trickles down to the supply chain, and the new dyes are coming in. So in this case, that's the tail wagging the dog, because that's the end point of the product market is demanding that the entire supply chain is changing. Exactly the same has happened in automotive industry. So it is possible in chemistry. And in fact, we're starting a new big program with many industries specifically to do that, looking at pharma. What if all the molecules which go into pharma are actually defossilized? So what changes needs to be made in the entire supply chain for that to be possible? So this is this kind of concepts appear in the literature now. I've just read a paper on this, well, literally today. So it is something which is out there, but it's not yet the mainstream.
There's a question that came in from the audience. So an audience member, D.A. Robinson, asks if there are certain universities that are leading in terms of educating chemistry researchers on circular development. I'm not sure if y'all have any expertise to weigh in on that.
I think Juliana has a good view on that.
Thank you, Chris. I was voluntold by Chris. But I think in terms of, because we are more focused on the molecular level design of green chemistry, but what we see is that usually like the universities that are teaching the students of green chemistry about green chemistry, they're also inserting like systems thinking. Yes, Alexei, Lofana. They're also inserting like systems thinking and the circularity aspect of chemistry. Also the side of like, okay, the molecule you're doing here in the lab is going to be a product eventually. And we think about the circularity, all of these things. So Lifan is a good one. I'm living in Canada. I'm in Brazil now, but also in Canada, we have the University of Toronto. They have a student group who actually is very focused on green chemistry. The students, they push the whole green chemistry thing. So I always talk about them because I think it's very inspiring to have students pushing these things to the university. So the University of Toronto is another one. There are a lot of universities around the country that are pushing those things. And I think it's a good way to get inspired by them to make this change.
Yeah, I fully agree. I also really like the Green Labs initiative. I mean, I think you were recently in Groningen, or at least teamed up with the university in the north of the Netherlands, and designing sustainable chemistry, benign molecules and materials. Obviously, that needs to be done in an environment, in a lab environment that is also adhering to those principles. And every pupil that is trained in such an environment will ultimately go into industry or remain in academia, and then continue that message and philosophy of how to work and that also needs attention. I still need to have some work to do at my own university, but it's changing habits, changing behavior is part of the game, and that is maybe one of the slowest things to modify.
You used the word green chemistry, and I remember that, from Polynastis at Yale from many years ago, and this is about circular chemistry. Are those two concepts interchangeable?
I mean, the mission is the same, and I think in green chemistry the concept of recovering products and recycling those into new products could be emphasized more, and that was the sole reason that I thought we needed another set of principles. But it's really making molecules in a closed loop system. Every single step needs to follow the green chemistry principles, but we need to create a loop for every single product, so that I mean, now in the energy transition we slowly shift away from carbon, because if you burn it you get CO2, but then we suddenly rely on all the other elements of the periodic table for batteries, windmills, solar cells, and many are called critical raw materials because we don't have a lot of them. And so actually I'm currently completing a paper that has the title From Critical Raw Materials to Circular Raw Materials, because if you can ensure their circularity, you basically avoid the potential problem there is.
Can I add a small bit here? I don't know whether Chris will agree with me. The circularity or the circular chemistry has a significant difference from our current way of practicing chemistry. That is, we have to find a way of dealing with mixtures, and the mixtures gets worse and worse the more you recycle the materials. Many metals cannot be recycled multiple times because they accumulate impurities, and after a while your performance goes down. And the same with polymers. You cannot actually, very difficult to get clean monomers out. Your impurities are there. You cannot run polymerization anymore. There are so many examples. It's very difficult to clean up solvents. So we have to actually learn very different ways of delivering the functions, maybe less perfectly, or maybe design a different way of working with mixtures and keeping them as such. So I think there is quite a significant shift in how we have to look at chemistry and what do we do with it if we really go to circularity.
Yeah, I fully agree. I think now the state of the art is, if you want to modify a property slightly, you throw in an additive, but like you said, that will mess up the recycling. And in the Netherlands there is a company that thought, let's improve the sustainability of mattresses. I mean, typically there are polyurethane and then different coating, flame retardants are added for safety, and they completely change that into a new product design based on PET, polyethylene terephthalate, all the different components, even the glue is PET. So one material and the flame retardant properties are actually induced by the same material. So even you don't need an added flame retardant, and that I really love, because it will. I mean, now it's more expensive, so that's another issue to tackle. But by product design, it truly adheres to the current standard of doing sustainable product design.
Juliana, I've got a question for you. Which step can we take to make chemistry more benign?
Thank you so much, Helene. So I think Chris mentioned a lot of all the steps that we could do, like this connection between circular chemistry, sustainable chemistry, and green chemistry. But also something that I push a lot, of course, is education. As we said, I think this is the very beginning of how we can promote change and innovation and technology. But also something that I push a lot, and I've been pushing throughout my studies, is like communication science. Often I think we go to conferences and people are presenting and we have no idea which language they're speaking, even though they're speaking English or whatever language they're speaking and we're supposed to know. Sometimes it's crazy. So I think like the communication aspect of the work we do, and actually explaining things to people in a way that people can correlate and understand, is crucial. And I think sometimes we forget about this because we're always immersed in our own labs, in our own silos, in our own environment. So I think talking about green chemistry, sustainability, circularity in a way that people can understand and relate and see the effects is so important. And as Chris mentioned, the goal is the same, the mission is the same. So talking about how we can make this change in the very beginning, how that impact our lives in a way that we can all agree with, I think that's the most important thing. So yeah, I think communication is like a very good way that all of us can do to promote that. My opinion.
No, thanks, Juliana. That's great. I don't think anyone can underestimate the importance of science communication. We have another question that popped up in the webinar chat from Romain Mirenzi. He says, "Hi, Chris. At the global level, how do you assess the progress towards the achievement of the Sustainable Development Goals in the 2030 Agenda?"
Yeah, that's a good one, and at the same time a really difficult one to properly do. It's the same that, for example, if you think of the 2030 and 2050 circularity goals, I mean, the city of Amsterdam wants to be 100% circular in 2050. Now, this is utopia, this is not realistic. But at the same time, setting those targets, only then everyone in the industry, governments, and is the regulation right? What are the incentives? Only then you start working towards that goal and start to solving all the issues that you bump into on the way. So also the planetary boundary concept that I showed, I use it always qualitatively to highlight the key challenges, what we need new and much better chemistry. And then, of course, we need to scale it up. And academia can not only do that, we need the entire society to realize that. The transitions always take more time than we want. But if you think back of renewable energy production, that is taken off. Solar cells are 99% cheaper than they were like 30-40 years ago. So change is happening, and there are many positive stories to be shared, but still there is work to do. And the sustainable development goals or other goals can be used as a guiding tool where we can put our action to and our energy on.
Thanks so much for that. It's a tough question, no doubt. Helene,
Oh,
did you have a question to ask?
I noticed another question in the chat as well,
Oh.
which is, are you using AI to look at new ways to advance circular design in chemistry? This is asked by D.A. Robinson.
I do.
I would like to, but I need AI experts, so like Alexei to realize that mission. But I find it truly inspiring, the advent of machine learning and AI as a helping tool to learn more, to train data sets, that we actually realize this. I mean, draw a molecule on the blackboard, predict its function as a medicine, predict at the same time its biodegradability. AI can truly help us in realizing that goal in the coming years.
Got it. Thank you.
Yeah, in the coming years, because at the moment biodegradability is still not really possible. I think we can design a function reasonably well. Certainly, if somebody asks us a molecule, ask us a question, can we design a molecule with a specific functional property, for example, light emission or something like this, or light absorption, then yes, definitely, that's possible, and it will be. We can even design a reasonably good synthesis path to that molecule. We now do it commercially through our company, exactly this kind of tasks. And our clients do ask us, can we do also biodegradability and the toxicity? And we say we will try, but at the moment we don't guarantee the success, because the models for biodegradability prediction and toxicity predictions are still way off in terms of quality. That's a big frontier for us to be able to do those, and it's an important target.
Yeah, and at the same time, it truly highlights the need from society for more sustainable molecules and materials, and at the same time the need for new knowledge. So we can only start developing that knowledge if we have more and more researchers on the topic who like to work in let's say systems chemistry and combine multiple disciplines, because it for sure is possible, but chemistry was never designed as such. So if we discuss the topic and inspire others, more and more research should be done and implemented at the industrial scale.
Yeah, thank you for the comment. It's really all about the data and what quality of data do we currently have about chemistry? How do we encode the knowledge of chemistry, the interrelationship between the molecules? How do we use all of that? Many of these tools, which are AI-based, are still relatively early days. We're now talking about integrating all of these tools with language models and so on, and it's amazing. The underlying AI tools are still a little bit flaky in many of the tasks, but they're getting better, and there is a growing community of people who are really interested in developing those methods. There is a growing interest from industry to find ways of sharing the data, generating the data collectively, because everybody now understands data in chemistry is extremely sparse and very, very important. And just to show what you could possibly do with the data, let's say we use, my company uses Reaxys data set for analysis or predicting synthesis paths and so on. We can now, with that quality of data, enumerate where all the atoms come from. Did they come from fossil carbon? Did they come from biocarbon? Did they come from circular routes and so on? And then the metrics of what the product is like, what goes into the product becomes really much, much easier. That's only possible with AI and machine learning kind of tools. But we know that our numbers is not very good yet because our data is not very good yet. We need to do quite a lot of work to make very reliable data sets for this kind of numerical analysis of chemistry. The less numerical task, like predicting whether the molecules will react or how they're going to behave in a particular solvent, is actually easier. It's been done. The more numerical ones are really a problem.
Yeah, a colleague of mine, Timothy Noel, is also, I mean, you probably know him, Alexei. He's also on that topic. And the other day, he also mentioned, like, in synthetic chemistry, you develop a protocol and then apply that protocol to 50, 100 reagents and make 50 to 100 products. But the protocol is never optimized for all of those individual molecules. And recently he focused on RoboChem as a robotic platform where you can actually per molecule optimize the reaction conditions. So if you use photochemistry for some reagents, you need high light intensity, the other low light intensity, low flow rate, high, and you can really optimize all the specific conditions and then get better yields. And more importantly, as Alexei mentioned, more reliable data that then can be used much more efficiently in machine learning.
That's a good advertising for his science paper.
Unintentionally, you brought it up. We should all work together.
I have a question on plastic. With all the concern on microplastic, what do you think is the future of plastic? Chris or Juliana?
Yeah, I'm not a polymer chemist, but I mean, I would say plastics are essential. We may design them a bit better, but if you think of plastic wrapping around a cucumber, it sounds odd. Why would you need it? But actually, it reduces food waste tremendously. And what you then need is obviously a closed loop system that plastic never enters the environment and is continuously reused. So yeah, there will always be a need for plastic. Wasting plastic, entering, letting plastics enter the environment or any molecule material for that matter, that is the problem that should be prevented.
I could probably say in a slightly different way. I don't think there is always going to be need for plastic. There will always going to be need for networks of molecules, and these networks of molecules create certain properties, whether this is strength or barrier properties or elasticity or something else. It doesn't have to be fossil-based plastic. It doesn't have to be cellulose. We don't know. In many cases, the problems which we are currently experiencing are not the problems of the materials. These are the problems of our economic system, because it promotes effectively free rein for whatever you can do with the available material, and then effectively oversupply of that material and stimulation of the demand for that material where it's not actually, shouldn't actually even be used there. And there are many examples when materials are used not where they were intended to be used, and not very appropriately, just simply because they're available in the market, and that becomes a self-fulfilled thing. So it's not a problem often of the material itself, it's a problem how it's been used. And Chris, I used exactly the example of the cucumber this morning, writing a position paper on green chemistry. It's not a problem of the polymer industry that the food industry is using polymers to protect the cucumbers. It really does increase the shelf life dramatically, and the food waste goes down. But it's a problem of the food supply chain. It just has to be different. If you redesign food supply chain, you don't need the plastic. So yeah, it's a wrong solution for the wrong problem.
Yeah, I agree. I mean, also I'm fully into the, for example, the ban on single-use plastics. You know, like we should create products that we can continuously reuse and recover, recycle. But now, if you think of plastic straws, you know, I could have always, you know, put them in the plastic bin and then they can be recycled after. But now they're paper-based with a plastic coating or a PFAS coating. Now they go into the general bin, and the rest of the package goes into the plastic bin. It's like, you know, which solution or which problem does solve this? You know what I mean? It's yeah, we need a really a proper analysis of the problem at hand, and then design a proper solution that is then supported by regulation and industry.
Fantastic. Well, we are coming up we're at the 2-minute mark. We've had great questions from our attendees. Thank you. And I also wanted to see if there was anything else that our panelists wanted to say regarding this really very riveting topic.
Well, I wanted to thank everyone for joining us. Chris, that was such a wonderful, thought-provoking presentation. And Juliana and Alexei, what great contributions you've made to the conversation. I'm really grateful, and I'm also hopeful that it's inspired, you know, us and whoever is viewing the webinar to envision a more sustainable future. So thank you so much.
Yeah, thank you. Thank you.
Thank you. And we do have 2 minutes left. If there's anyone who still wants to, who's attending and still wants to ask questions, they are welcome to. So we have another question from Romain, which is Rwanda banned the use of plastic bags 2 decades ago. Can this policy be adopted by other countries?
Yeah, I would say so. Yeah, I think in the EU there is a focus on banning single-use plastic. So this I think fits to that purpose. But we need much more. You know, you can a ban on carbon-based fuels would be an interesting one. You know, to solving the climate crisis. But a ban on nitrogen or phosphorus-based fertilizer will never work because those elements are essential for crop growth. But you know, there you need a closed-loop system. So I would say for every product, like Alexei mentioned, you know, engineers learn product design. But I, for example, to date, I have never learned that. So there is so much on the educational side of things that we can and should improve.
Banning is not always the right thing, right? You can ban the wrong stuff. Maybe encouraging the right behaviors and the right business models is much more productive. If you change the business model, you are much faster to win. Everybody is much happier.
That's definitely something to think about. I mean, that's what makes this topic so interesting. And yeah, I hope that there will be more discussions about this in the future. And I want to say thank you to Worcester Polytechnic Institute and to all the panelists, Juliana, Alexei, Chris. We really are grateful for having you come and share your expertise with us. And of course, to all the attendees who asked questions as well, and to Anita and Rob too. And with that, I want to say thank you again. Have a wonderful day, and I'm sure we will all be in touch soon.
Thank you
so much.
All right, thank you. Bye-bye.
Bye.